Hello, my name is Alex Shushu. I am a research assistant at Polytechnica University of Bucharest. I am happy to present the compiler we developed for the KNEX Vector Accelerator from the lab of Professor Stefan. The idea of my project is to compile efficiently C-sequential programs to coordinated vector assembly for a system using the KNEX Vector Accelerator. We handle portable programs, which basically means we generate vector code to run on various KNEX processors of different widths or vector lengths. A few words about our targeted architecture. KNEX is an easily customizable vector processor designed to run efficiently basic linear algebra subroutines. Customization means mainly that we can synthesize the processor with a number of lanes or execution units between 32 and 4096, which makes the architecture very wide. Each lane of the processor contains a 16-bit integer ALU, which is good for power consumption, but we need to emulate a lot of types that are not supported. KNEX has predictable performance because it has no caches and has a separate vector scratchpad memory. I currently work with a processor synthesized in an FPGA, and here it exhibits low power consumption. For 128 lanes at 100 MHz, KNEX consumes at most 1.5 watts. The Opinka LLVM compiler we develop relies on the LLVM framework. Just to mention, Opinka is an assembler and coordination library for KNEX. We add a new backend for KNEX and implement efficient emulation of arithmetic operations for unsupported types in it. We also extend the loop vectorized paths of LLVM in order to generate coordination calls for KNEX, add a symbolic static memory allocator which relies on an existing symbolic range analysis library, and so on. The compiler generates a C++ program containing coordination calls and vector assembly kernels. This is vaguely similar to OpenCL code. We then take this program and compile it with GCC for the host CPU. We now present some important experimental results. Our setup uses a KNEX processor with 128 lanes synthesized at 100 MHz on a Xilinx 7020 FPGA. The speedups we report are with respect to one ARM v7 core at 667 MHz and a 128-bit Neon SIMD unit integrated also in the Zinc SoC. On the left, we present speedups of a few benchmarks such as dot product, matrix multiplication, sum of square differences for three different element types. First, 16-bit int, the native type for KNEX. Then two types emulated on our processor. 32-bit int, for which we actually don't achieve acceleration, as we can see in the respective figure, unless we use, for example, a wider KNEX of 512 lanes. And a 16-bit floating point emulated by both KNEX and ARM. In the right-hand side figure, we present speedups of a few 16-bit integer benchmarks if we run them on KNEX processor instances with a number of lanes between 32 up to 1024. We notice, for example, for the sum of absolute differences, that the speedup grows slightly asymptotic on this logarithmic y-axis due to the non-negligible I/O overhead of KNEX. We invite you to try our open source software tools for the KNEX processor in case you don't have access to a synthesized KNEX. We also offer a processor simulator that is very easy to use. Thank you very much for your attention.